Okay, our next speaker is going to be Harry from Swansea. He'll be talking about reasoning about trains.
The railway logic, we prove it to be correct using formal methods, and I take the result of that and prove it to be correct in Rocq. So to kind of give a bit of an overview of what I mean, so we take the interlockings, so the logic that controls the trains, and we do testing on it against some standards. And because we don't want the trains to crash, there's about 7,000 to 10,000 properties or so. So this takes quite a long time, and a way of getting around this is that we can encode our interlocking into some kind of format for verification, do the same with the safety conditions, and then in theory, once you run it through the verification tool, if this passes, it should go through testing fairly quickly. And bear in mind, testing takes, say, 6 weeks. This takes an hour or so. So you speed the process up. And if you have to make a mistake, so if you make a mistake and have to start again, in theory, you should get the error earlier. But the problem is, how do you actually have trust in what your verification tool is doing? Because they're very complicated and not many people actually understand the deep logic of it. We perform some proof checking, and the idea is, again, that you still have the encoding. You take the result of the verification tool, run it through another tool that checks its output, and then once those two say yes, you can perform the standard testing that is obviously needed to get the accreditations and all that. This could be done two ways. We could make a checker ourselves, but what we do is we use Rocq so that in turn we can prove that the checker that we are making is also correct, which adds another level of safety and sort of validation to the whole overall process. And why are we doing this? Well, you have SMT solvers. In our case, it is Z3 from Microsoft. They're often applied to these safety critical systems. However, there could be flaws in optimizations that are used to produce said results, and you don't know if they're incorrect because it's so complicated. I genuinely believe there's one guy in Microsoft who knows everything, judging by the GitHub repository. If something happens to him, I'm in big trouble. That's all I'm saying. And we want more than a true or false result. And if we do this proof checking, we get an actual certificate. And so my goal is to build a verified proof checker, which will independently verify Z3 rather than Z3 just saying, yep, it's great. And why this matters is it increases the confidence of using the verification tools in that overall tool chain I showed you just now. So, Z3, what does it do? Well, it produces some proofs. And when it produces a proof, it gets back a proof log. And it is made up of these 4 types for the SAT logic, so that's what we focused on to begin with. We have simply assumptions, which is what the initial interlocking logic was. We have RUP steps, which I'll go into in more detail in a second, but this is using resolution to derive new clauses from anything that was existing. Eventually, you'll get to a point where it derives a contradiction, the empty clause, and therefore you know it's a valid proof. You have Tseitin steps, which simply perform the Tseitin transformation to take something that is not in a CNF, conjunctive normal form, and make it into CNF, but critically, nothing changes in terms of the satisfiability. And then if ever we produce something that makes something redundant, we can delete it. So I said about RUP, well, this is the foundation of the whole proof format, so reverse unit propagation. We take a clause C, which is made up of some literals, and it's valid if you take every single one of those literals, negate them, add them back to the original formula, and by this unit clause propagation, it makes everything refutable. And for this, we've developed a proof structure to show this is correct. We called it a tree proof because it looked like a tree. I'm not very creative with names. And what this means is, say you had A that was derived by RUP, you could add the negation of it, the A, and this shows that via one cut and then another cut with another existing clause, you would get a contradiction, and therefore that A would be a valid step. With Tseitin, well, it's slightly different to what usually happens. Z3 takes the fresh variables that are usually generated and puts the original formula back in, which is quite nice because it makes everything a tautology. And then what Z3 does is it uses these tautologies in RocqPL to cut down and learn some more steps. And what this does in our checker is we validate it by matching it against any of the known patterns, because there's about 8 patterns, and if it's not one of those, it simply can't exist. It also has some clause learning, where there's 2 components. There's the left-hand side, this antecedent, and the resulting clause on the right-hand side. The right-hand side is the bit that's used by Z3 for further steps, and if it knows something in there is already false, it just cuts it out to save RocqPL some time, but it's still based off the original tautology. In terms of proving everything to be correct, the first thing we did, as I said earlier, we have a checker that runs to check the unit clause propagation for RocqPL. I built the tree level structure, and then for every step of the way, we basically proved that we have a corresponding tree. So from the start, you'll have a proof of the start. Every time you do a cut, you'll have a proof of that cut. And at the end, you'll have one big tree that showed from the start, you could show an empty clause. And then we could feed this into the overall proof system. So this is all, as I say, all done in RocqPL. And the basis of that is logical entailment, such that if you have a set of formulas and you have another clause which is part of it, if one is modelled, the other one has to be as well. So we want to show everything to be logically sound, and in our proofs we have these assumptions, which is what we start with. We have the conclusions, which is what is derived. Every step of the proof log adds another one of these conclusions, and we simply say that if the assumptions are modelled, the conclusions must be modelled. And every time we add something or remove it in the deletion case. And then the critical thing at the end is if the unit resolution derives the empty clause from the original set of assumptions, it therefore means that the assumptions have to model falsity, which obviously can't happen. So we have that the original formula is unsatisfiable and our proof is therefore valid. So in RocqPL, what we did, we went through each step and we showed that this relation holds, such that if you add an assumption, if you discover an assumption in your proof log, because it's on both sides, it keeps the entailment. With RocqPL, because you're deriving something from something that was already existed, and if you have this relationship before, again, you're still going to have it. Tseitin steps is a new technique where we replace the Boolean variables with the originals, which make the tautology, and if you're adding a tautology to something, you're still going to get your relation. And deletion is if you're removing something that's redundant because you've already got a sort of unsat core as such, you keep your relation, or the opposite of that. Some actual proofs, because I thought it'd be a good idea to show those. So with the theorem on the left is sort of the main thing we came up with, such that if the checker says yes, you could preserve that A modelling C relationship with logical entailment. And then we made another set of proofs such that if the checker passes and it comes back with an empty clause, i.e. that the last step was indeed a proof that we've derived the unsatisfiability, the original set of assumptions are unsatisfiable. If you want to see all of this, you can. It's not that exciting. Okay, so then comes the exciting bit for what I thought was exciting and why I was really intrigued by Matthew's talk this morning, because we're trying to extract this so we have verified code, and currently we're going to a camel, and industry would love it to go to C++. So when that came up this morning, I was like, yes, this is great. So what we did is we evaluated the proof checker for applying results from 2 techniques that our partners use. One is inductive verification and bounded model checking is the other. Bounded model checking is far more complicated, hence why the number of lines for the proof logs are much larger, but that was basically to stress test this thing. In reality, inductive verification is what it'd be used for, and that takes about 30 seconds, which they were quite happy with. And what I should stress is that when I told this to my supervisors, they didn't believe me. The proofs are literally all the rewrite steps to get to one point where it goes, RocqPL says, yep, you have a contradiction. Don't quite know why it does that. Who knows? Okay, to summarize, what we're doing is we have some independent verification for Z3, such that when we apply our verification tool to the railway, we can confirm that it's actually doing what it says it's going to do. And in terms of keeping the correctness, we're using Rocq, because otherwise, if I just wrote it myself, there's a very high chance that there would be some errors. This way, at least we have some formal correctness alongside it, which, as I say, adds another level of confidence to the verification process and hopefully does make the railways safer, which I'm sure everybody would quite like. So the next steps for me are to formalise and prove the further Z3 rules so that we can expand it to the SMT logic, and that will allow us to use this on all of our verification tools, not just the one that we've currently applied it to with the SAT logic. For this, we're trying to make a foundation that's sort of a plug and play kind of approach, so that as new rules are developed, it's as easy as possible, kind of how we did it with the whole logical entailment proofs. And the last stage is to basically perform as much industrial testing on the final checker. As much as proving it to be correct with Rocq is fantastic and brilliant, the industry and the engineers, they like testing. So if we can have the proofs and the testing, they'll be really happy. So, thank you.
Do we have any questions for Harry?
I was just wondering how it relates to the existing SMT COC works which verify certificates of SMT.
Yes, so we've looked into that. The sole reason for doing it externally was that Z3 introduced a new format, and the industry wanted something that was basically built from scratch that they could take away. And as I say, I'm going to do testing, but they want to basically line by line this, and they know what's been done effectively. We have looked into it, and it is a basis for some of the things we are doing. And if there's ways to cheat and not do it again, then I will use it.
So I've talked with people who do certification before, and they're often very hesitant to pick up formal proofs. Do you have ideas on how, like, are certification authorities or the people doing the testing interested in these level of proofs?
So the people who so the best way I can answer this question is they're not. But because in the sense that in the UK, when the industry tries to say they've got these proofs and they go to Network Rail, for example, and Network Rail go, well, it worked first time, that's impossible. But in the sense that that's why they want this tool, because it's a way of making something a proof without it being a proof, if that makes sense, because it's something they can see running, they can understand line by line, and it's almost hidden the proof from them. That's the way we sort of described it.
So if I understand well, the specification of what you proved is, in fact, it's important. Myself, I would not really trust the fact that you just say it's been proved. What is important is what has been proved.
Okay.
So the specification is the basic rules of the SMT solver?
So what we're proving is the rules that the SMT solver uses in order to derive unsatisfiability. And when it does that, it prints back this big log. Mm-hmm. And it says, I've done this, I've done this, I've done this. And what we're checking is that for every single rule, if I applied what it has done, given that rule that it's told me it's done, is that possible?
Okay, thank you.
We have one last question. If the other speaker wants to come up.
Yes. There are several formats for exporting SAT proofs from SAT or SMT solvers. Mm-hmm. Can you, you said you wanted to use the recent Z3 format.
Yeah.
Can you very quickly summarize the main differences, for instance, with respect to the DRAT format, which is used by other solvers?
Yes, so, best way to describe it. In the short way of looking at it, sorry, I'm used to explaining this in like massive answers. I can.
Maybe we can take this off.
Yeah,
that's probably the right way to do it. Okay, let's start here again.